Hello navigators, welcome back. In today's lecture, we are going to start a new course on combustion modeling. In this particular lecture, I am going to talk about a brief overview of combustion modeling, different modeling landscapes that are there in combustion modeling, and what are different solvers that are present in OpenFOAM. Let's get started. Combustion is a complex physiochemical process. It involves fluid flow. If something is burning, there is some substance, some gaseous mixture which is burning. This will give rise to some kind of a flow. You will have fluid flow, and this particular fluid flow will often involve turbulence. Then there will be heat transfer, because if something is burning, it will raise the temperature of the mixture surrounding it, and this will involve heat transfer from the substance to the surrounding. Then there will be chemical reactions. For example, CH4 is burning, it will react with O2 and it will give rise to some H2O and some N times H2O and M times CO2. Apart from these two, there will be strong coupling between thermodynamics and transport. For example, density is a function of the volume fraction of the species and temperature, and there will be some evolution of species, and there will be a corresponding transport equation for this particular species, and this will be linked through thermodynamic relations to density. From a CFD perspective, combustion is a multi-physics problem. You have chemical reaction, heat transfer, fluid flow, and strong coupling between thermodynamics and transport. As well as it is a multi-scale problem, because the chemical reaction, they take place in a very small time scale, in around 10 is to minus 10 is to minus 6 to 10 is to minus 2, and the fluid flows, they take place in 10 is to minus 2 to upwards. Therefore this is a multi-scale problem. That's why combustion is difficult to simulate, because chemical time scales are very less than the flow time scales. Indirectly, the heat release from the species is going to alter the density, the pressure and velocity. Nonlinearity is already in the momentum equation, and on top of that we have more terms coming in from the chemistry point of view, and there is stiffness because of this very large difference in the time scales. The practical application includes internal combustion engines, gas turbines and burners, fires and safety analysis, and explosions and deflagration. We can classify combustion in two regimes. The first one is premixed combustion, where we assume that a certain region has a premixed mixture of fuel and other species, and then we are just interested in that how the flame propagates from a unburned region to a burnt region. And there is non-premix combustion, where we are interested in finding out that if there are two species, one is fuel, another one is, let's say, oxygen, and they are mixing up, then how this particular combustion is going to take place. Then we have to take care of the fact that what region we'll assume as a completely mixed region, and in that region only a chemical reaction will take place. In pre-mixed combustion, the fuel and oxidizer are mixed before ignition, and flame propagates through the mixture, as I explained, and flame speed is a key parameter. The typical examples of pre-mixed combustion are spark ignition engines and laboratory Bunsen burners. Then we have this non-premixed combustion. Here the fuel and oxidizer, as I explained before as well, that the fluid and oxidizers are initially separated, and the reaction rate is controlled by mixing. This mixing is estimated by different models. The flame stabilizes at stoichiometric surfaces. This basically means that if there is some flow that is going on, then the fuel and oxidizers are assumed to be fully mixed at turbulent scales, and at this level only the reactions take place, and then you can have different kinds of diffusion that also can be modeled. A typical example of this is jet flames. then pool fires and industrial fires. There are two kind of combustion. First one is laminar and then turbulent. In laminar combustion, the flame structure is dominated by chemistry and diffusion, and you can resolve it directly because the flame structures are dominant by chemistry. You can directly resolve it. But in turbulent combustion, you have turbulent wrinkles and stretches in the flame, and this requires turbulent chemistry interaction models. We'll also see that how we can model this when we are modeling the flame speed and how the flame is evolving with time in between the unburnt and burnt region. There are two kinds of methods that are usually used. The first one is direct numerical simulation. It resolves all the scales, but it is prohibitively expensive for real systems. Therefore, we have to use engineering CFD, in which we use either the Reynolds average numerical simulation or large eddy simulations, and it relies on convention models. Different modeling strategies that are dependent on accuracy and cost are: this one is finite rate chemistry. In this, each species is evolved and the chemical reaction takes place at turbulent scales, where we assume that the mixing is uniform and isotropic, and there only the chemical reactions takes place. And then you have this reduced and phenomenological models, where we solve the flame propagation combustion as an averaged volumetric phenomena, and then we focus on the pressure buildup and the temperature buildup in the simulation. The third one is the one where we are interested in solving the simulations for pre-mixed fuels, and we are just interested in how the flame propagates in the flow and how the temperature rises and different related phenomena happens. Let's talk about these models in details. In finite rate chemistry, we solve the transport equation for all the species, and then the reaction rates are obtained from the Arrhenius kinetics. The coefficients for this equation are obtained usually from experiments and literature, and it is the most physically detailed approach, but this is very computationally expensive and stiff because the chemical reaction rates, the time scale for this is very less than the time scales for the fluid flow. Then this is best suited for laminar flames and weakly turbulent reacting flows. Then we have reduced and phenomenological models. It avoids direct solution of detailed chemistry, and here the flame behavior is modeled using additional equations. Basically, this uses a flame surface density model. Here a volumetric model is used. So for a certain volume, what is the combustion rate that is used to evolve the fluid flow as well as the heat exchange. A turbulent flame speed model is also used, where a detailed flame speed is not solved and a model is used instead. This particular method is widely used for turbulence pre-mixed combustion. The next type we have is a flamelet and FSD based approaches. It assumes a flame structure similar to laminar flames, and chemistry is pre-computed and tabulated. Here the turbulence affect the flame through scalar dissipation. There is a strong reduction in computational cost. This one is also used for a pre-mixed fuel, and a common variant is steady and unsteady flamelet models. Here also a flame surface density transport is used, but the unburnt and burnt field is solved for the entire flame, not volumetrically. There is a flame front which is solved and advected. This is best suited for turbulent premixed and non-premixed combustions. Key challenges in CFD combustion are, as we have already talked about this, but let me reiterate that a strong coupling between flow chemistry and temperature. Then the stiff chemical source terms are involved. Chemical source terms I'll explain in the next few slides, that what are the source terms that come from the chemical reactions. Then there are large density variations because these chemical reactions give rise to very large variation of temperatures that give rise to large density variations. Then we have a range of spatial and temporal scales. So spatial scales in the sense that we have to go up to the turbulent scales to find out the fully mixed regions where the chemical reactions takes place. Temporal scales in the sense that the chemical reactions that are there, the time scales in which they take place are very less than the time scales in which the flow physics happens. Then the combustion modeling is always a balance between physical fidelity, because we need accuracy in terms of the chemical reaction and the flow that is developing, the heat transfer that is going to take place, and the numerical stability, because we have a large range of temporal and spatial scales. We have to make sure that the numerical method is stable for the lowest time scale and lowest spatial scale. And the computational cost, of course, because when we have a very small time steps, then the computational cost increases. And similarly, when we have to capture a very fine spatial scales, then also the computational cost increases. In OpenFOAM, it has various combustion solvers. The ChemFoam is a chemistry solver only. It is a zero dimensional solvers, and it can only solve chemistry. So you can define your ODE that you want to use to evolve the chemistry in a zero dimensional cell. That means you don't have to find out fluxes, etc., and you just have to evolve in time. Then finite rate reacting flow solvers are ReactingFoam and row reacting foam. This one is incompressible, this one is compressible. Then you have pre-mixed combustion solver, which is XiFoam, G dynamic foam, and Z engine foam. All these solve for flame front, and they assume that the combustible substances are pre-mixed, and they are just finding out that how the flame evolves with time. And there is this final one, which is fire and explosion solver, in which a volumetric premixed combustion is solved. You have FireFoam and PDR foam. These are the two variants, and both of them focus on different aspects of a flow. For example, PDR foam focuses on the pressure development and the temperature variations due to any explosion, and whereas this fire foam, this takes care of the flame front and the modeling between the turbulence and chemistry. An overview of how a combustion solver works is as follows. You have to solve for mass conservation, then momentum conservation, and then the species transport and energy conservation. I'll also explain that where the chemistry source terms are introduced. These are augmented by turbulence modeling. Turbulence modeling is augmented here in the momentum equation, and the chemical reaction models are augmented in the species and energy transport. Here in the continuity equation, there is nothing much that comes from the chemistry, but the density of any cell is a function of temperature and the fraction of species in that particular cell. In a way, the species present in a particular cell affects the density of that cell. Then you have this momentum equation where there is nothing that comes directly from the chemistry. You just solve this equation with any turbulence model that you have, but there will be density changes due to the species that is present. Then there is species transport. Here the source term due to chemical reactions comes from this rate of chemical reactions. This is the chemical source term that introduces the stiffness, because for this the time scales are very small. And the turbulence diffusion is modeled. This is the diffusion that takes place for the species, and this should be modeled, and this is usually modeled using Fick's law. And then in the energy equation, you have, whenever a chemical reaction takes place, you have some enthalpy that is added to that particular cell. This heat release couples the chemistry and the flow. This is the heat release, and this is the enthalpy of the flow. It strongly affects the density and pressure of the flow. This is the chemical kinetics, which is just the rate of species that is being generated as a function of this reaction rate, which is obtained from the Arrhenius equation, which is this. And these coefficients are determined using experiments, and they are already present in the literature. This is the source of stiffness in the combustion solver. This particular equation, it should be computed for each and every species, and this motivates the reduced chemistry model. Then the modeling is required for turbulence closure, as I explained in the momentum equation. Then the turbulent scalar transport is the species transport, and then in the turbulent chemistry interaction in the species transport equation only. And then the thermophysical properties that are there, these sometimes need modeling when the actual values are not available. Different OpenFOAM solvers, they use a different closure choice, and depending upon what they want to achieve from that particular simulation, and therefore there are so many solvers for combustion modeling. In this particular course, we'll understand the physical assumptions behind each solver, and then we analyze the governing equations and the closures that are used in a particular solver that we are going to discuss in this course. And then we will learn the solver selection for practical problems. We'll solve a small test case, and we'll also talk about that why the selection of that particular solver is done in that particular test case. While solving, we'll gain hands-on experience with OpenFOAM. I hope you'll enjoy this particular course.
Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.